All right. Good morning, everyone. Okay, I'm very happy you're all here because I think this is going to be a great session. Let me just set it up by something I always say to my incoming graduate students. So I'll tell you how this works. When my incoming graduate students come in, so they're already math majors and they're starting graduate school, I ask them the following question. I say to them, okay, suppose you had a young sister or brother. They were maybe 8 or 9 years old, whatever that age is, and they had learned how to do addition. And they learned all about adding, and they understood adding, no question. And then you said to them, and they just learned multiplication. So you said to them, what do you think 3 times 5 means? And they said to you, okay, that's 5 plus 5 plus 5. And you said, what do you think 5 times 3 means? Well, that's 3 plus 3 plus 3 plus 3 plus 3. See? And he say, there you go, see? Right? That's the point. And you say, well, are they the same or they're not the same? Oh, they're the same. You say, well, why are they the same? Well, a smart kid will tell you they add up to the same number, 15, which is right. Now do you say to them, what do you think 235 times 493 means? And they'll tell you 230, whatever I said, 495 times. And now you say, what about the other way? And they take it backwards, right? They take it backwards. Are they the same? Yeah. You say, why? Commutative law. Mm-hmm. You say, did you ever do those additions? You know, add up all those 325, 495 times? No. Did you add them up the other way? No. How much would you bet on that? Would you give your life for that? Yeah. Why would you? I don't know. So the interesting thing in math is how do we know when we know it? That one example I just gave you while you're sitting here, now don't get too distracted, but there's a good answer to that. In fact, I'll tell you what the answer is. And by answer, I don't mean a proof or anything, but a good reason. And you can look in this room and you can see the reason. Because you see how many chairs there are across here? So what is it, 10 chairs across here? And maybe there's 35 rows that way? Well, if you count them by columns, that's one way to do 10 times 35. And if you count them by rows, that's the other way. And we all see it's the same number of chairs, right? So that would be a good reason. You know, none of my students ever think of that. They can never tell you that, right? So what I'm trying to say to you is, yeah, we have formal ways that we know things, but in math, we should at least have a pretty good reason. Now, I'll make just one more comment. If you go back and read in Euclid, you know, we all have heard that there's an infinite number of primes, right? So you know prime numbers. There's an infinite number of them. If you go read in Euclid, what he says is, if there are 2 primes, there's a third. Or maybe he said if there's 3 primes, there's a fourth. Whatever. That's all he ever said. That's all he ever said. And he explains why, if you already know that there's, say, 3, I think it's 3 prime numbers, he says here's why there's a fourth. And we can talk about that another time. But for us, all of us, that's completely persuasive. If you go read it in Euclid, you'll immediately believe that there's an infinite number of primes. You won't doubt it for a minute. So you know it in that case. On the other hand, these days, we have a proof of that that's called using what's called the axiom of induction. Do we need that? Is that important to us? And if so, why? So we have 4 panelists here who do very different kinds of mathematics and come from very different backgrounds. And I'll let them introduce themselves and maybe make a couple of comments about that, and then we'll go on from there. Okay, so that's the starting.
Peter Sarnak. I guess I was introduced earlier, so I don't want to bore you. So I should make some comments about this question of what do you know when you know it, or something like that. How do you know?
How do you know when you know it?
I took the question to be a little different.
Well, that's okay.
So one, and I'm assuming most people here are seniors or graduate students or beyond.
Some sophomores and juniors.
Sophomores, junior. Okay. So when I was learning, at least at the undergraduate level, often you would be introduced to some slick modern theory, algebraic topology. That was a good example. It could be Lie groups or something like that. And what many modern writers do is they want to show you how clever they are. They want to show you, look, I can prove this, and look how slick this is. And then you look at it and you say, gee, this is kind of frightening. How would I have thought of this? And when you go back and you look and you understand, you realize that this is a long evolution. This didn't just fall into this person's head. It happened through a lot of other people writing, and then each person's trying to be cleverer than the last one. So the moral of the story is, if you want to learn a subject, you should read the original. So you might be taking a class, but go read Riemann a little bit. Go read Hermann Weyl. Everybody in the theory of Lie groups wants to give their proof of Weyl's character formula, which is one of the great results in that subject, where whatever Weyl touched, he changed. He had this kind of golden touch. He himself is not so easy to read. So what you do is you read this account, then you read Weyl, and then you go back. And if you go back to the beginnings with algebraic topology or something like that, you'll see how the subject evolved, and how the most important thing you have to keep on asking yourself is, could I have done that? And the answer is probably everything if you evolved in the same way. But if you just dropped in the deep end, it looks intimidating sometimes. Now, there are some steps which are just revolutionary, where the whole way people are thinking changed. A good example is John Nash. He proved something called the embedding theorem. The story goes that he asked what's a very difficult problem, and he got from these people like Levinson and Louis Nuremberg and people who had been thinking about this problem, that this is a hard problem, and so he was challenged by this. And then the standard way of proving any theorem like that was some kind of implicit function theorem. And he went into Levinson's office explaining how he's going to solve this problem where he was going to lose derivatives. He was going to go from one space to a worse space. So Levinson said, just prove that you can put the circle isometrically in some high-dimensional space, and I'll listen to you. This is what I've heard from a number of people, including Nash. So the story there is that he had invented this Nash scheme. Later, Moser understood this relation to other schemes. But it was completely orthogonal to the way everybody thought. You lose derivatives, and he gained it from some other means, something called Newton's method. So that kind of thing, if you go back, you would not see that step. So they are very great steps of that type. But many of the textbooks at the undergraduate level, and especially at the graduate level, they are just too slick in my view. And you do well by reading, or at least learn how it evolved, and it will help you understand that this is something that is not so surprising, and that most people like you and me who are interested and love math could maybe not invent it, but could see that it's not out of the ballpark. I don't want to take too much time. That was one way I interpreted the question. Of course, as Phil explained there with commutativity of multiplication, you don't need a proof after you realize what the idea is, and that's true with most mathematics. So you learn theorems and you learn proofs, and they come, like I like to say, in ordered pairs. You should always know the proof, but you don't need to know the formal proof. You just need to know the idea. The idea is usually much more convincing than any formal proof. And when you talk one-on-one and explain a proof, that's where you learn it. You know when things work. Sometimes they're a little vague, but you should always do exercises and check out special examples. Mathematics is very concrete, but the conceptualization is what makes it attractive. So I think since you asked about history, I used to be maybe a professional chess player, and to me that was the only interest in high school. But when I discovered math, in high school in South Africa, which was a very problematic time then, mathematics was not something that people did for a profession, that anybody who I knew knew that. Physics, yes, because there was this guy Einstein, but math, I don't know. So chess, yeah, because you go there and you compete with some older guy when I was a young guy, and you enjoyed beating an older guy. That was all about competition. But when I got to university and learned about abstract mathematics, the fact that you have concrete problems, but the best way to understand it, like, say, linear algebra, that you look at an abstract vector space and you think abstractly, and then things become very clear. the conceptually, abstraction's very good. But if you just think conceptually and you don't know how to compute, you are useless. It's like somebody saying, I want to do this, this, and this, but I don't have any tools. So really you have to find the balance between doing exercises, computing, say in differential geometry. Everybody wants to just explain things conceptually, but you go to a physics class and they'll be raising and lowering indices and not telling you what they're doing, but they can compute. You've got to be able to do both. The concept makes life easy, but if you just conceptualize, you don't take a basis in linear algebra, you won't get very far. So you can say, look, I've understood this, but you need the tools, and those tools, some of them are boring. I like to teach boring classes. You've got to learn tools so that you can execute ideas that you might have later. All right, let me stop there.
That's great. Christine.
Okay, thank you. So I think I also interpreted the question as, if I'm an undergrad, right, how would I know that I understand math? And so I think, what Peter also mentioned, that you need to be able to teach the material to others, right? And so if you are in a position of maybe, tutoring in a math class, whether it's Calculus 1 or Algebra or Real Analysis, then that's really when you get to learn the material, when you are teaching it to others and explaining it, right? And that's good because it brings up questions that you yourself need to address, right? You'll know whether you know something or not. And then another thing, I think when I was an undergrad, what I did, I studied a lot in groups. And I went to a big school, 50,000 students, and so it was kind of like, the professor was there, but not really. But when I got to the upper division courses, the classes became much smaller. But I would study a lot in groups. And so, for classes like abstract algebra, real analysis, and others, I enjoyed the subjects, and, it was very interesting, but I needed others to work with, right? And so, we'd work through the proofs together. You'd stay up late at night just trying to come up with a proof, but it was exciting. And then you'd see the pattern, you go, wow, that was pretty neat, right? And this is how the assumptions work. So that's, I guess, another thing when you do proofs, to ask yourself whether you need certain assumptions or not, right? And then when you go to graduate school, that's where you'll be, coming up with new theorems, right? So your advisor's not going to say, look, I think this is a theorem, or this is a known theorem and prove it now, but rather you'll be coming up with some conjectures, and you'll need to determine what assumptions you need, right? And whether you can loosen an assumption so that it makes your proof stronger, right? And that to me was pretty exciting, coming up with conjectures and then proving them, right? And I guess also in your courses, when your instructors teaching you all about theorems, then it becomes exciting also when you can come up with a conjecture yourself, and then you realize, oh, that's the next theorem in the book, right? And so it kind of helps you and think, I'm thinking along the right directions, right? And so you're not way off, and it boosts up your confidence also that you're going in the right direction. And then I switched from undergrad. I switched to applied math. And so in applied math, there's more, you also have theorems there to prove, and you can come up with conjectures and prove those. And so in those courses, you mainly have more like convergence analysis to determine whether your algorithm will converge or not, right? And so yesterday, I gave a talk, and somebody asked, well, how do you know you got a local minimum? Well, there's some convergence analysis based on the numerical method that you're using. And then you also try and start your code with different iterates to make sure that you can obtain the same local minimum, right? So those are some ways that you can figure things out, right? What else? I think that's it. All right. Feel free to ask questions later.
Yeah, we'll have lots of questions.
Okay. I'm Pat Hooper, and I'm a professor at City College of New York. So I was thinking about this question, and when you know something in math, and there's some easy answers, which one of them already came up, which is, when you can teach it to somebody else. I think that's an easy answer for when you're clear you understand something. Another one that maybe is really important is, I think if you have a research problem in mind, like something you're thinking about, then some problem you really want to solve, if you've learned something, if you know that you can make progress in this problem, like somehow, that sort of makes it clear that you've learned something. And then, so somehow, but then those are very special cases. Like maybe you're taking a math class that's oh, so maybe before I leave that subject, like this sort of suggests also that it's a good idea to get involved in research at some point, like talk to faculty and get some, ideas of things that interest you and some problems and stuff that keep in your head, and that'll sort of direct you and sort of how to understand things in math. So if you're taking some class and it's not, you don't have somebody to work with and talk to about the things you're learning, and you also don't have a research problem, then a good substitute is like, can you solve a problem you haven't seen before? I guess and actually in math there's just endless problems out there. I think you have your textbook, of course, but then any class you take, probably there's 100 textbooks on the subject or something, so you could just pick up a different textbook. So that's one way to know you solved it. But in some sense, I think these answers are not sort of that satisfying because, so maybe I'll just share one story from my past when I was an undergraduate. So I got really excited when I got to school, and suddenly I could take these really hard classes. So I enrolled in one of the hardest classes I could as quickly as I could, and of course I floundered. And then I go to the professor for office hours, and we talk maybe about my test. I can't remember, and he told me I don't think clearly. And I thought this was pretty neat because it meant he could read my mind and see how it worked with that. But on the other hand, he was probably somewhat right. And I think I do think one thing is you shouldn't, maybe the question is maybe not quite completely a perfect question in the sense that there's some gray area between when you actually know something completely down really well and you're actually learning stuff and and it's hard to really understand that there's some sort of between completely understanding something and not understanding it at all. But in fact there's some sort of gray area, and so I think when I was thinking about this, I think this question, the topic we're on is one of the most important things in math, and so when you're taking classes and things, I think it's important to be able to learn to have a skill to know whether or not you know something. That's not developing that skill is probably the most important thing you can do, because once you can develop the skill to know if you know something or not, then you can test it, and then you can just experiment. Once you can test if you know something, then you can sort of think about things creatively and move and think about things in a new way, and then you can see if when you're thinking about it in this new way, you now understand something, right? So yeah, I don't know. So I guess that's the main thing I wanted to say is, yeah, I don't know. Maybe I'll just stop there.
Okay. I wish you just kept going and not got to me. I'm Don Cole at the university. I'm a professor at the University of Mississippi, and a longtime member of this conference, been coming for years. And so I told Phil he could put me on any panel that he wanted me to. And when he put me on this one, I said, "What?" I would have said anyone but this one. But for starters, will all in the audience who are faculty, would you just raise your hand? Do we have any faculty out there in the audience? Or just a couple of faculty members, because I want you all to be as much as part of this conversation as you have gotten us up here as well. When I was in graduate school and just finishing up, and was going to graduate, was getting ready to graduate. For financial purposes, I needed to add one more class, my very last semester. And I added a class, and I think I might have even audited the class. I wasn't interested in it at all. It turned out to be maybe a geometry class. And so I know I had to work in my other classes, but I didn't have to work hard in this class because it was an audit. And that semester, I think they had maybe one of the early copies of the Elements, which was Euclid's book. There in the library, you couldn't touch it. You'd have to go and read it and let them turn the pages and all of that. And I could care less. I just kind of looked at it. But somehow in that class, I was just blown away and amazed because we're talking a couple thousand years ago, and I don't know what you were doing a couple thousand years ago, but I certainly wasn't thinking about this one. And I was sort of thinking about how this stuff was organized and sort of brought forward, and even today it's still relevant. And it probably doesn't meet today's standards 100%, but it would be close enough. Where you had, today we'll have these undefined terms. we don't try to say what a point is, what a line is. You know, Euclid tried to do that. And then he had some defined terms. And then he ended up with some axioms and some proper, and then from the axioms, he grew some, you know, propositions, if you will, or theorems and proofs and whatever. And it was just kind of amazing to me that 2,000 plus years ago, that's how mathematics was done. And that set the pace for mathematics today, even. And so when I thought about this topic, I thought about that sequence and where you start off looking at definitions and actually trying to understand the definitions and the concepts. And I knew, I don't know how I ended up on the last spot on this table because I knew that everybody's going to say everything good by the time it got to me. And so all I can do is kind of repeat some of that. So you start off with those definitions, and as the first speaker mentioned, I used the word history. And if you have some type of historical perspective, it makes all the difference in the world because even some of the definitions, where on earth did they come from? You know, did God just drop them down? How did somebody come up with such a definition? But if you just sort of look at the historical aspects of it, then you'll see, oh man, well that's a natural definition to start off with. And then and all of mathematics is going to kind of go back to these little axioms and the you know, if you will, that you kind of assume somewhere along the way. And again, where do they come from? Would I have thought of those? And most of the time, I think that you would have. Are they reasonable? You know, kind of ask yourself all of this, you know, these questions, and ask your instructor some of these questions along the way. And so it kind of makes for a conversation. You've all heard, and I know I'm talking too much, but I don't care. You've all heard that mathematics is a language. And everybody in here probably knows English, but you do not know English in a vacuum. So if I put you somewhere in outer space, it's only unless you're able to talk to someone else that you understand that you know and understand English. And it'll be the same way mathematically, unless you can talk and confer with someone else. And that's why we started tell you to take this class and talk with these people and get study groups and find someone else to sort of talk to it. And along the way, your English will improve. You know, your mathematics will improve. You know, the physicist, when he has an idea about something, what does he do? He's going to run into the laboratory. Or the chemist, he's going to devise some experiment and going to see if it makes it work. Well, the mathematician is going to do the same thing, but he's going to do it probably with a little cheaper, with a little piece of paper and a pencil, and something that he's going to call a proof. And I've seen many proofs that claim that they proved something, and I didn't believe it, or I couldn't see it. You know, I couldn't follow the logic. And I think that was said a little earlier, that sometimes you have to graduate to that. You have to read something else first. Excuse me. And sort of build up to it, if you will. And that, you know, that logical part that's going to make it click for you, sometimes make it resort back to algebra, something that you know. Make it resort back to calculus, something that you know. Make it resort back to linear algebra. And the more that you go, the higher that you go in math, then when you resort back to your basis of something that you know, then that's when you feel like you know it at the next level. Let me say. Long time ago, when I was a little boy, 2000 in Euclid's days, 2,000 years ago, I thought I knew something when I got an A out of the class. And somehow, when I got up in grad school, that just wasn't good enough. I could get an A out of the class and didn't feel like I knew anything. It was much, much more than that. It was when I was, thoroughly convinced, somehow, that I could follow the logic, that which one is given first? Is the epsilon, if you're given the epsilon, and then can I find the delta, or what's the negation of that, etc. When I asked myself all of these questions, and I even remember when my parents thought I was going a little weird, when I would, etc. I would never even go to the bathroom without a book and take advance. And that was part of all of my learning experience. So I'll stop right about there, and we'll probably and I'll probably say some of these things again, but we'll have questions and whatever. But those are my opening comments. Thank you for the occasion.
I'll just tell one story, and then we could open it up to, when I was in graduate school, how many of you read a book or had in class a book by Walter Rudin? So I was lucky enough to know him. He turned out to be he was at the University of Wisconsin when I was there. I was there in 1970,
I knew Rubin as
1967.
well.
Yeah, you knew him as well.
Yeah, I
he-
talked with
and
Rudin.
Mary Ellen as well. His wife was wonderful too. I should talk about that too, because she was
She's a great
very
mathematician
strong
in her own right.
Mary Ellen Rudin in topology. But Walter Rudin had a wonderful history. He had actually escaped from Nazi Germany, and then he was a young man, and he was in England, and he went back and fought with the anti-Nazis in France, and he's quite a remarkable guy. And he was German, and German Jewish, and he was quite strict. So when you first got to know him, you could be a little intimidated by him. And I had, of course, from his book, which was brand new at that time, and he wasn't the one teaching it. So I never met him, and I went to see him because there was a problem that I couldn't do in the homework. And so I went and asked him. And he was very polite. He said to me, "Did you read the chapter?" That already made me nervous, right? Yes, I read the chapter. He says, "Do you know theorem so-and-so?" I said, "Yes." He said, "Can you state it?" I said, "Yes, I state it." He says, "Can you prove it?" I said, "Yes," and I proved it for him. He said, "What side of the page was it on?" I didn't know. He said, "You don't know it well enough yet." And so actually, he was right. When I really understood that theorem, I had no problem with the whole. So I just thought I'd do it. So now, we'd love you to ask questions, anything you want to ask. Yes?
This is a question for Dr. Hooper. You talked about a gray area. I think there's that phrase that you never really know math, you just sort of get used to it. What are your comments on that?
I don't know. I do think. I think there's a gray area, and then there's it. That's sort of my view. I wouldn't say that there's. Well, I don't know if is that the right thing. Yeah, I don't know. I think that's a good approximation anyway.
I think what some of these folks said is right. We heard it in a number of places. First, what Peter said, which is that if you know a lot of examples, and all of those, and if you see why those examples work, in other words, if you've done a lot of computations, usually you know why the thing is true in general. And the other comment, which I liked from both folks, and I always tell this to my students, is if you can really teach it, you probably know
yes, that's
it.
right.
You
That's
probably
right.
know
That was
it.
the other
Because
comment.
the thing is that you're gonna be prepared for any question, right? And I think the trick in mathematics, at least as it's been done since the time of Descartes, is we're trained to be skeptical, which is not something that is in every culture. In a lot of traditional cultures, we're not skeptical, right? We don't ask questions. And certainly in theology, in general, we don't ask questions. And in a lot of the older, we don't, right? And some of the older subjects, we don't ask questions, right? We more or less become people's students, and then we replace them and do what they did, right? And so in mathematics, and all of science, right? The whole point is to be totally skeptical. It was Descartes was known as a radical skepticist. So I think if you're in the habit of questioning everything, and you have no more questions, you probably know it at that point, right? So, yes?
So going off of what you just said, what would you say to someone who says that, well, if you always have questions, which we do in mathematics, there's always a next question, then you never really know it.
Yes, I think probably you never know all of mathematics.
You never know all of
right?
mathematics,
But-
that's right.
But probably when you have no more questions about a particular thing, probably you know it, right? I would think. What do you all think?
But isn't there like always another question?
There's always another
Yes.
question leads you to something else, I think. Yeah,
Yeah,
yeah. What do you all think?
yeah, I want to hear from others.
Yeah, I mean, I think what you said is right. Yeah, I mean, there are always questions, right? So even if you work on a problem, you can always improve on that problem. So another question is going to pop up, right? So I mean, yeah, I agree with what Phil mentioned. Yeah.
And some questions are not going, that you ask are not going to be answerable within the framework of that subject. It might be answerable only in the framework of another area of mathematics. But the question is still a viable question. And mathematicians are just very curious folk. And by nature, we just kind of ask questions, and the joy of asking and the joy of solving and answering that question is the joy of mathematics. And let me stress that word joy, because many of us would not be in this area if we didn't get some joy out of it.
Other questions? Let me stand up and see. Yes, ma'am.
Did you ever fail or need to retake a class? And if so, did you approach the class a second time with a different perspective?
Ah, that's a great question. Yes, sir.
In math, or in chemistry, yes. Just dropped out.
That's why you do it, man.
So I think many of us, so it's connected with this gray area. So suppose you're a first year undergraduate and you're taking quantum mechanics in chemistry, where the person's trying to teach it without having partial differential equations. And so they're giving this kind of descriptive version, which is, for some, I think for most mathematicians, very unsatisfying. And in a situation like that, you're in this kind of gray area where you sort of vaguely know what they're talking about. But however, I think what is good is to be in a gray area where you don't quite know what's going on. So let me change a little bit and say that I always encourage all students to go to every colloquium at your university. Presumably, so when I was a graduate student, the speakers were awful. Every talk was awful. But and there was no training in speaking, and the more that nobody understood you, the better people thought it was. But that really has changed. It's a dramatic change. In other words, in most universities now, I think for a colloquium, the speaker is chosen because they actually can string a few sentences together. And usually they're very good. Now that colloquium might be in a gray area for you because it's outside your area. And so you will maybe even not understand the details, but it's amazing how much familiarity is part of understanding. So you hear the same things over and over again. You don't quite understand them, but you start to see there's a picture there, and you sort of begin to feel that if I need to understand that, I probably could go and find out what it's about and how to understand it. You always have to put in the time and the hard work. But it's very important to understand different fields also, because as was pointed out, sometimes the solutions of the most interesting problems, and this has happened repeatedly in recent years. I mean, if you look at the solution to Fermat's last theorem or the Poincare conjecture, especially the Poincare conjecture came from partial differential equations, nonlinear partial differential equations. The people who were trying to do the problem, topologists had never worked in partial differential equations, so it came out of left field. And that is something that if you aren't aware of certain areas, you might not even be able to incorporate it into your thinking. So I think the gray area is not such a bad thing. You should always have, now let me just talk a bit about more when you go to graduate school, you will have to focus on something at some point, because you're going to have to become an expert, world expert at something. And as was said, there are certain things that you feel very comfortable with. You must have you on a mountaintop and you understand this particular area and you become an expert on that. You work, you might make a contribution there, hopefully make a contribution there. But then, now I'm much older, so I can look back at chemistry, where I couldn't, and I now understand the mathematics that's required. And then you can venture out, but you always have your areas that you feel that you know as well as anybody else. And there you have a comfort zone, but it's important to push yourself in the gray area where you might not know, but where you open to ideas there, and if you need to go there, you can go there. So I also think it's important to keep problems of different level when you're working. You should never take a problem where you'll get no joy out of solving it or no satisfaction. Then we're not just doing this for the sake of producing papers and saying, look, I wrote a paper. So if you know how to solve a problem before you start, unless somebody else is desperate to see the solution to that problem, you're not going to get much satisfaction. So you should have a problem, but you should never not think about the greatest problems. I think it's very important that there's a dogma. That's very hard, don't do it. One of my luckiest moments was to take some well-known conjecture of some very famous person and say, maybe they're false, maybe they're wrong.
Yes, yes.
And they were wrong. And once I decided I was wrong, then progress came very quickly. So the point is that there is a dogma around, and people say, oh, X tried that, X says that doesn't work. You should question dogma. Don't question the truth of the Riemann hypothesis if you want to talk to me. But you should question things, because sometimes there is this just people regurgitating that can't be done that way, and sometimes that's completely wrong. So I like this gray area. You should put yourself in a gray area more than you're comfortable with.
I want to piggyback off a couple of things that you mentioned, and also the question that came forth as well. It was about failure, and probably all of us up here, and all of you all out there have probably failed in one way or another, and failure just gets you closer to your goal. Is one way to sort of think about it. But you also mentioned something about the word time and time and investment in time, because I'm convinced that just about anybody can do mathematics, and just anybody can learn mathematics. For different one of us, it's just a matter of how much time you want to invest. And I had to invest a lot of time to get to the same level as this individual, probably much more. I sort of enjoy at night when my wife and I are there in the bed, and she's reading and I'm reading, and she's a sociologist, and she's just turning her pages, flip, 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 and I'm on this page this week, next week, and I get criticized. But it is a time investment. But I tell you what, once you have it, it is there forever, and then a day.
And I guess, yeah, I'll recount, Peter made me realize of an issue. When I was an undergrad, I was, taking a real analysis class. And so we proved that, the real numbers are, real numbers are uncountable, right? Mm-hmm. And so I remember going back and telling my professor, I think they're countable. And, so he goes, I said, I'm gonna study this, right? I said, I think they are. And so I go back, da-da-da. And then, I come back to him, I said, I think you're right, but it was that questioning, right, that I really thought, I said, I think I might have a way to prove that they are countable, but, they're not. And then I remember, I remember being, a graduate student. I was taking linear programming class, and so our instructor tells us of this story of George Dancing. And so he's considered like the father of linear programming. Or optimization. And so the story goes that, and you can find this on the internet also, George Dancing, he passed away maybe 10 years ago, right? So kind of recently. And so the story goes that, George Dancing was a graduate student at Berkeley. And every day, every time there was class, his professor would list a certain, problems on the board for homework, right? And so George, goes to class this one day, but he arrives there late. right? And so the problems are already posted on the board. He writes down the problems thinking that they're homework problems, right? And so he goes back and he works out solutions and, studies them. Weeks later comes back to his professor and hands in, these solutions. And so he tells his, professor, here are the solutions to those problems. And, his professor says, just put them on, on my desk. So he does. And so, weeks later, the professor comes and knocks on his door. He says, you just solved these unsolved problems, right? And so the more of the story there goes that if you don't know that they're if you know they're homework problems, you'll say, yeah, they're doable, right? Maybe a little bit difficult. But if you believe they're unsolved, and if you hear the word unsolved, you might say, oh, they're too difficult. Who has tried them already that I'm not going to get them? And so George never listened to that story. He just thought they were homework problems, right? So that made up part of his, dissertation.
I've got a few homework problems for you.
So look at, you can look it up and get the
Beautiful.
full story.
Yeah, I can say something about, about failure that's actually related to this, the topic. I think one of my most embarrassing moments, I think, was when I was a graduate student, and I began working with my advisor, and but I was the last of maybe 5 students at the time, and we took turns presenting papers basically in front of for everybody else in the group, and so I prepared some paper and prepared some presentation, and and it's exactly like what happened is I had something prepared and I worked through it, and someone asked me a question, and it just destroyed. I couldn't answer the question. And so it is exactly that thing. I thought I knew this, and I didn't know it. Somehow, and I guess one thing I want to say about it is so you learn from that. So I learned, I learned that somehow whatever, I can't remember exactly what I learned, but but certainly from whatever rubric or whatever I had to understand if I knew it or not, I learned that I didn't know it, and I think that was very valuable probably, so it wasn't a complete loss of an experience. It was sort of embarrassing, but it wasn't a complete loss. And the other, so I do think it is important to take your these classes you're taking. It's good to push yourself into this gray area, and because in the end I think that skill of being able to tell if you're right or wrong is the thing you're really trying to develop. And so maybe it's even reasonable to say your goal in taking a class shouldn't be to get an A. It should be to learn learn the subject, and even better is to learn to know when you learn something is probably exactly the thing you want to be doing.
Since none of these people will answer the question about failing classes, I will. So when I was in 8th grade, I was taking algebra, was the high school level algebra, and for various reasons I was not able to sort of keep up with the class, and I was not doing particularly well. And I didn't know why I was not doing well, but I kept going to the teacher for help, and at the end of the semester he said, look, I should give you a D or maybe even an F, but I'm going to give you a C because you're trying so hard. And when you go to high school, I know the high school you're going to, just tell them you took the course from me. They won't make you take it again. And then you can take geometry. I think you'll do okay in geometry. And then you'll never have to take math again. And you won't have to worry about it.
That's what you did, right?
And I knew that wasn't right, and luckily the next year I took the class again. I took the class again from somebody, and it turned out that my problem with algebra wasn't the manipulation of the variables. It was that I couldn't do word problems because I thought, like everything in mathematics to me at that time, word problems were formulaic, and I just needed to figure out what is the formula to do a word problem finally. And one very wonderful teacher said to me, David, you're really good at this, but you do have to read the problems. If they're word problems because each one is its own problem.
Yes.
And after that, all I wanted to do was word problems. I went to the library. I took a book out of the library and did every word problem because I was so excited that I could do it. And I was so, and I got a PhD in word problems. And it wasn't until probably after I got my PhD that I realized I was so angry at that guy. But that's why I was determined to be a math major and determined eventually to get my PhD.
So why don't you just called us his name, and we'll go find him.
He's long departed, but it's Mr. Leary. When I went back to one of my high school reunions, I told one of my classmates about this, and he said, "You mean Mr. Leary, who kept a bottle of whiskey in his desk?"
Other question? Yes, ma'am.
Is there any math course that you took that was so difficult that made you question pursuing a career in math? And how did you work through it? Because I'm going this.
Which course is it that you take?
Just linear algebra because my professor is terrible, but.
Yeah. So if I just comment quickly, that's exactly the thing that you should let happen to you, because in fact, sometimes you get a bad teacher. Let's be honest about it. Sometimes you just get a bad teacher, and it alters your perception of whether you're good at this stuff. And in fact, it's not being well communicated. I know, I didn't say who the person was, and I won't, but when I had my analysis course, where I just told you about, I found that course extremely difficult. And in fact, I didn't flunk it because it was a graduate course, but I got a very, very low grade in it. And that turned me to do abstract algebra for my, and number theories for my career. And it was after I was out for 10 or 15 years and had some success in research that I finally understood that the things I really wanted to do badly involved understanding analysis. And I went back and taught the course so that I would learn it, just as we said, learn it well enough. I figured if I taught it, I would really know it then, right? And so I went back at Iowa and I taught that same course that I had gotten a very bad grade in, because I thought, now I have a good reason to know it. But I have to tell you that for 10 to 15 years, I had an attitude about that whole part of mathematics and thought to myself, oh, that's a stupid way to do things. I could do this a much better way without it, and that kind of thing. So you should never let it bother you if something is hard for you to understand at first. You should never let that bother you. Instead, you should probably ask people who like it what it is they like about it. And let them tell you, it's your peers. Just say to them, why, that stuff is really hard for me, linear algebra. This is really hard. Why do you like that stuff? What is it about it that makes it so easy for you? And you might try that. Other questions? Yeah.
So, in my, like, a lot of you have spoken about, like, teaching others and talking to others about math in order to get a better understanding about it. In my university, the math community is, like, very dispersed, like, among students. So, what I'm wondering is, like, if you find, like, how would you, like, I'm not sure if you've been in that position, or if you were to be in that position where you're an undergraduate student, but you can only find, like, 10 other math majors in your university. How can you try to, like, find people to be able to have, like, a lot of conversations with in order to get a better understanding?
It's a very good question, because I think you learn more from your colleagues than anybody else. People your own level of development, that's rarely where you learn.
Yeah.
And that, if you don't have numbers, that's an issue.
You know, the people here, if you make some friends, I'm just saying,
Yeah.
you know, you can use Skype now. I mean, really,
Yeah, that's right. You can
one of
use the
perfect to
electronic
find people here. Other
media.
thoughts about that?
I mean,
Go ahead.
there is, I mean, how about in your class? I mean, is there,
So it's like, my university has 120 math majors is a generous number.
okay, but I mean, you're still taking a class with 20 other students, or?
And none of them want, like, there's not like a community there. It's like, they're math majors, but they're just like, oh, I'm getting my degree and leaving.
Well, you're the community builder.
Okay, other questions? Yes.
So as we move through our educational and our professional careers, how do you suggest dealing with imposter syndrome as we navigate this gray area?
That's a great question. Did everybody hear that question? Okay, so maybe you don't know that phrase. So there's a phrase that's common these days. It's called imposter syndrome, where you feel like you don't really belong there. And people say in the minority community that that's more common, and among women also. So somebody, I remember speaking to somebody, for those of you who know, I remember I spoke to a woman who became a very strong mathematician. And she was telling me that at her graduate program, she'd get up every morning, she'd go to her office, and there was a faculty member who was a well-known person who also came in early. And he passed by her office. And it turned out he was very happy to have her there. He'd come in every morning and he'd talk with her. And she said every time she heard his footprints, she was convinced he was going to come in and tell her it was time for her to leave, that she wasn't up to the thing. So that's, I think, what imposter syndrome means. And I like everybody to talk about that a little bit and say to what extent we've all felt that way and that we didn't belong and what the best way to deal with that would be.
I've heard that term quite a bit, and I could probably certainly testify that I have felt that way, and I felt that way quite a bit. And it perhaps speaks to one's character or whatever, that somehow you realize that you have to push through that. And there have been people who made me feel like I didn't belong, but I only needed one person, just one, to make me feel like I do belong. And I've been able to find that individual. Sometimes it would be really nice if that individual found me. And that would be perfect, and that has happened. That's been happening in my class, and happened external. And there have been times for which I've had to reach out. And so, and that's not always easy. It wasn't easy for me to do, but I realized that, okay, to survive the situation, that's something that I'm going to have to do. Just like when my body get cut, I tell my body, okay, you got to heal, body, and it does. And so I think that if you're determined to sort of go through the program, that you can find that one person. And if you find that one, you're going to find another. And when you find another, you're going to find that third one. And you find that third, you're going to find out that there'll be an infinite many who would like to see you there as well.
Okay. Well, I obviously, I'm a white male, so I mean, sometimes like I haven't experienced it the same way. I mean, I do think, I mean, one thing I want to express is I think this is like a really important issue, from my point of view, and especially when we're talking about the importance of to understanding math. It's based on community, and communicating with other people is a huge part of that. So I just want to say it's really important, and I think hopefully your professors and things sort of realize that this is an issue, and you should hopefully feel comfortable to go to them and discuss them with them about it. And I think it makes these things more, it's just fair to say it does make things more challenging if you have more trouble connecting with people because you don't feel like you're part of like the main group, say in your class or something. And I can see this as being a serious issue. Maybe.
Well, I just want to add that, like, imposter syndrome, I guess there's also that component of not feeling good enough. Not necessarily that you don't belong. So,
Oh, yeah.
That you were, like, you're a white male, but there's also, like, we've all been at that point where, like, maybe I'm not as good as X, Y, or, like, in this respect, in our capacity to do math. So I just wanted to make sure that was also, like, considered.
Yeah, thank you. Yeah.
Yes, so I think, what Clarissa mentioned here is good. Sometimes you feel that you're not good enough as somebody else, right? So I think that's sometimes how I, feel, when I go to conferences, right? And so I'm working on my own problems, and since I've worked on those problems, I feel like I know it well, and so I figure then it must be easy for everybody else too. But I have to remember that that's my problem, right? I'm the expert in that area, and so I know that well, right? And others may not be able to understand it, and so, I'm doing okay, right? That I don't have to be doing the high-level work as others, so maybe that work may not be high-level, but I may be considering it high-level because I'm not in that area, right? And so, I know my area well, and I can communicate those, well with those people in my area. So that's how I kind of, portray it also, see it also. And I guess, what some of the speakers have mentioned here, you've got a network. So when you go to conferences, now that you're at the Field of Dreams, you need to network and get to know other people also, right? And share your ideas. And feel comfortable that, when you are with others, you can talk math, right? Because I know sometimes as women, because I've been with other, in other meetings at our university and all, we've mentioned how as women, sometimes we just talk about our children. Oh, so you've got so many children, right? And da-da-da. And so we need to be talking about math also, right? What do you do in math? What's your research area? What are you working on, et cetera. And so we need to feel very comfortable talking to, all different genders about those things and meeting new colleagues and networking and, and so forth.
Well, I think there is no mathematician who won't run into another mathematician who they will feel inferior to. There's amazing talent out there, and what's beautiful about mathematics is there's a lot of room for doing what you really want to do.
as I was saying before, is you want to aim high, but you've got to get satisfaction of solving problems that you get satisfaction solving. So I don't think you should worry about seeing people who are better. There's a fellow called Carl Ludwig Siegel in number theory who was anybody. There's a famous story of a Jewish mystical study called Gershom Shalom, who was in his class. And he wrote his father wanted him to be a mathematician, and he wrote back saying, well, there's this guy in this class, and if I have to be like him, I clearly can't do the subject. And that's the way everybody who came across Siegel felt. And he went and then studied mystical Jewish studies, became very famous, but still was kind of always looked back at this fact that this guy in the class kind of frightened him. And there are people like that who are just extremely strong, and they will make you feel that they are extremely strong. And then there are people who are even better, who make you feel that you're part of this whole picture. That's right. So they're different personalities. They're going to be people better than anybody. Everybody eventually might be on top at some point, goes down. I don't think one should view it as this kind of competition. The beauty of mathematics is there's room. It's not such a big community. And as was said, we talk to each other, and we only can function by being talking to each other in the same kind of language. And there's room for invention and for developing the subject and for teaching the subject for many, many people, all of which are successful stories. So I think you should just enjoy and make sure that, or achieve what you can achieve. I don't think. Now, at Princeton, when I first got there, there was an issue of this females feeling outside of or not being inclusive, especially at the undergraduate level. There were often cliques and certain very talented females who didn't even apply to graduate school because they weren't part of a clique. When I was chair of the department, this was something that I would never tolerate. So I hope that people, as you said, go to the professor, but of course they are problematic people. It used to be much worse in the 80s and 90s. I would hope that now that people are aware of this, if there were actual people in the class who are offensive to other people, that's certainly something that should not be tolerated. But we do have a problem of cliquiness, and it's not easy to address.
Yeah, if I could just briefly say, because we all are so eager to do this work, all of us, everyone in the room. I think that cultures like mathematics have a lot of inertia built into them. That is to say, we don't know how they got the way they did. We don't know why certain people were singled out to do it, not just white men, we know that already, but certain kinds of white men who have certain ways of seeing the world, and that kind of thing. We don't know that that was inevitable. We don't know that it would have worked better if we wouldn't have had minority folks involved or women right from the beginning. We have no way of knowing how this set up the way it did. But there's people invested, understandably, in keeping it the way it is, who are not particularly terrible people. It's just that they're so invested in being part of this profession that unconsciously they were afraid of any change. So you may experience that as a certain contempt sometimes, or a certain distancing, and you may have this feeling correctly, absolutely, as Dr. Cole was saying, you may very well have the feeling that you're dealing with people who wish you weren't there, or would find it a lot easier if things were back the way they were. And you have to just always remember that's their problem. It's not our problem. None of our problem in this room, nobody up here, and we have a whole variety of folks here. You have to, when you get that feeling, my own self, being a male, it would anger me. I've been through that as well. It would anger me. A little bit of anger is not a bad thing. You know what I mean? It's better to be angry than to put it down on. A lot of women blame themselves. A lot of minority folks. Just say, look, I don't need to deal with these kinds of people. As Donald said, you just need one person in that university or in that department who's not like that. And go to that person and work with them, and just keep your head down, and remember you love this stuff, and just we'll change it together as we move forward. Don't let it get to you. Just keep talking to each other. That's what I would say.
Yes. And like I guess in terms of closing remarks, I chose mathematics because it's difficult, but it's not impossible.
Yeah.
And if it wasn't difficult, I probably wouldn't have chosen it, and everybody else would have. And that's one of the things that kind of distinguishes me. I chose the difficult path, and it's not impossible. Finally, there's no elevator to success. You got to take the stairs.
I think we have one time for one last comment. Yes, go ahead.
I had a follow-up question. So imposter syndrome is most of the time framed in this, like, you actually do belong here and just need to keep pushing through it. How do you tell the difference between that kind of imposter syndrome and the slow realization that maybe this really isn't for me, maybe I would be more suited in a different field or a different area?
Yeah, I know I'm just commenting on that because we do this in Iowa a lot. That's a question we ask ourselves. The thing is, you don't know you belong in math. The way you find out is whether you love it. It's a question of love. So if you love it, then there's no imposter syndrome. At whatever level you do it, it's the thing you should be doing. If, on the other hand, you come from let's say a 4-year school, right? And there's this great opportunity of doing statistics or anything like that, and you haven't seen it. Then if you start feeling in graduate school, oh, the people here are very different than me, they think differently than me, it may be that you need to switch fields and do something different, right? So that's something that mentoring is about, and I just close by saying, find yourself someone, in the Alliance, you all have mentors, and when you go to one of our graduate programs, you'll have a mentor. But if you don't have a mentor, drop us a note or look for somebody in your department, because that's a good discussion to have with somebody you trust. That's the way I would say it. Thank you very much, everybody.
I concur.